So as we get into the first lecture for our second module here, we're going to be covering the topics of stress and strain and axial loading. So objectives for this section here, we're going to introduce stress and strain, take a look at normal strain under axial loading, talk about the stress strain diagram, how we design that, how we develop it, what we can gather for information from that, and with that we're also going to take a look at the modulus of elasticity. From there we're going to get into some statically indeterminate problems and discuss involving temperature changes into some problems as well. Now within this module here I'm going to talk about a couple different applications, relate this to some of my actual research and tensile testing, look at some key equations that we'll be utilizing in the homeworks, example problems, and possibly your future exams, and then go through some problem solving techniques. So the first thing I want to take a look at here is stress and strain. So the sustainability of a structure or machine may depend upon the deformations in the structure as well as the stresses induced under some type of loading. So statics, as we've seen before, analysis alone is not going to be sufficient for this. So considering structures as deformable is going to allow us to determine the member forces and the reactions which are statically indeterminate. Determination of the stress distribution within a member is also going to require the consideration of deformations in the member. So all these deformations are really going to come into play within this chapter. So this chapter is going to be concerned with the deformation of a structural member under, we're just going to take a look at, to begin with, to keep things simple, an axial loading. Later chapters we're getting into some other more complicated loadings, torsions, and pure bending loads. So as we get started, the first thing I want to introduce here is normal strain. So the way in which I'm going to introduce this is through a couple different diagrams and represent some of the key equations and how they relate back, how we can relate our load, our area, and our stress. So if we take a look here, we can see into this first figure over here, we have this column right here, and we can see this is undeformed on the left-hand side and deformed in part B on the right-hand side under pure axial loading. So we can see we have down here, we have our cross-sectional area right here, A. We can see we have our deformation right here, our D, and this is the change in our overall length of this column, this member right here. So the original length here is L, and it changes an additional length of delta right there. We can see when we apply that load, that's when our delta comes in and it deforms here. So you can see part C is now moved down that distance delta right there in the column right there from that applied load. How does this relate to a governing equation right here? Well, we can say that our stress is equal to this load right here, our load right there, divided by that cross-sectional area right there, and this would be our stress. Now, how does this relate to strain here? We're talking about our normal strain. Well, our normal strain here is going to say that epsilon, or our normal strain, is equal to that delta, that deflection, how much extra length we have on that after we apply the load, divided by the original length, L here. So this is what's important here to understand the difference between how much it's deformed, the extra distance it's stretched there, and the original length, and make sure we have that denoted when we get into some more complicated experiments and problems as well. So now that brings us over to figure 2.3. So the difference over here at 2.3 is we're going to say that we're going to apply twice the load. So twice the load is required to obtain that same deformation here because we've doubled our area here. This is 2 times our cross-sectional area there. So we need twice the load to get that same deformation if the area is twice as big, our cross-sectional area there. So what we can see now, we come down here, how does that translate into a governing equation? Well, we can see here, here's our stress again now, but 2 times P, or our external load, divided by 2 times that cross-sectional area. Well, you can reduce that down, our 2's cancel right here, there's still load over area right there. Now, what is our deflection? Our deflection here, our strain here is still equal to that deflection D, which is the same divided by L. So we can see here, this is still going to be the same there because we have 2 times the area and 2 times the load. So now, and we go to 2.4, rather than doubling that cross-sectional area, what if we were to double the length but leave the cross-sectional area the same? So cross-sectional area is still going to be A, but now the length is 2L as compared to the original L over here. Well, the deformation is then going to be doubled when the rod length is doubled while keeping the load and the cross-sectional area constant. So you can see our P and our A are the same. The only thing that we've changed here is our length here, so it's double the length, so we're going to get double the deformation here, and this relates down to the equation here. We still have that stress is load over area, so there's our load, there's our area there. That doesn't change, neither of those change. What does change is our original length and our deformation, so epsilon is equal to 2 delta over L there, where our 2's can still cancel, we're still left with delta over L as the actual ratio. So the next thing I want to get in here now is a little bit of material testing relating directly in this problem here to the stress strain test, or in this case here is really we're dealing with a tensile test. So we have a universal tensile testing machine here for specimens. This is a classic type of specimen here. And if you've ever ventured down to the basement in Vody, you can see we have a really old version of one of these down there in the basement. It's been retrofitted, and we do have I believe now the same or a similar computer, and it is the same brand as Tinius Olson down there. But back in the 90s, when I first came to the University of Vermont, we had a dial gauge that we used to control this, and had a little needle for our output that we'd actually have to record this down on paper when we were looking at it for load versus displacement. So these are your specimen samples here, and you can see now related to our previous slide, we're talking about length and area here. So you have a known cross-sectional area right at the center here based upon that set diameter there, and you have some gauge length over here, which is our initial length of the test specimen here, which is what we're calling here our undeformed gauge length, L0 there. This is placed in here, and it's a little bit hard to tell within this one, but if you look up here at the top between this head, so this head right here is moving by these two lead screws right there at a very slow rate. And it's stretching. The specimen is right in there, and you can see it looks like they got an extensometer connected to that as well, because there's two different ways that we can measure the deflection on this here. One, we can tell by how far these lead screws have gone and calculate the deflection that way. If we want something slightly more accurate, then we can hook on an extensometer right onto our test sample across this undeformed gauge length right here, and that will measure a lot more accurately, a lot more sensitive, the deformation in that specimen right there. Now there's a couple other machines that we do have now that are a little bit more updated in Vody. We have an Instron machine, and there's also a smaller 1,000-pound Test Resources machine, both of which I've used before, and I'll share a little bit of my experience and some of the testing that I've done with those as well. So this leads us now into stress strain diagrams. So what we can get from those tensile tests on the Tinius Olson or the Instron or the Test Resources, whatever the testing system we're using is, we'll see some results like this. So we can see here in photo 2A, we have a ductile material tested here on part A with the cross-section area necking. So you see the necking going on right there, and one that's actually reached failure there and ruptured here in part B of our photo 2.4. So what does this look like as far as our stress strain diagrams, and how do these physically relate here? So in figure 2.6, we have these stress strain diagrams for two typical ductile materials here. One, we have a low carbon steel, and part B over here, we have an aluminum alloy. So what we can see is we have our stress up here. So again, this is our load and area we use, we've seen from the previous slides, in order to calculate our stress right there. And down here, we have our deformation right here, which again we recall is based upon our deformation and original length of our test specimen right there to calculate both our stress and our strain to create these stress strain diagrams. Now a lot of times what you may see live on the screen for a lot of these is force versus displacement. So just make sure that you're taking a look at the right things, and you're not trying to calculate things that you need a stress strain diagram for, like your modular elasticity, off a force displacement diagram. You do the calculations and form the right graph before you start gathering some information off it. So what we can see here, we can see the elastic limit here, purely linear range right here as it ramps up under small deformations over here on this side, small strains. You can see that load or our stress jump up really quickly along that there, and we can see it kind of peaks and drops down a little bit right there. So this is what we're calling our yield right there. Then it starts increasing up here again under what we're referring to as strain hardening during this section from point 0.2 to 0.2, and then we start to see where we have this necking occur, this necking region here, and we get another peak, and it starts to go back down, and boom, breaks right there at the rupture right there, at failure at that point there. Now this is one type where we have yielding and then our strain hardening here, but let's just take aluminum alloy here. Well, this is going to act a little bit differently when we do our tension testing on aluminum alloy here. So we can see we go straight up in our elastic region right there, reaches right up here to our yield stress right there, then starts to slowly come over like this here until it gets up to the top, hits a peak right there, peak stress right there, and all of a sudden it starts to ramp back down. Boom, we have failure right there. So let's take a look at a generic one over here in a little bit closer detail. So we have our stress on our y-axis, we have our strain on our x-axis down here. Well, our Young's modulus we can pull from this. We've already talked about that just a little bit in the intro to this module here. So our Young's modulus is going to be the slope of this linear region up here up until we get to our yield strength, and we start to see it come out of that linear region there. So in this here, we have our rise, change in our y direction over run, which our rise is going up with our stress, our run's going over with our strain right there. So we have rise over run. So we can calculate our Young's modulus right off of our stress strain curve based upon the slope in this region here. So then after your yield stress from there up until you hit your ultimate strength at the very peak of this here, we have our strain hardening portion of our stress strain curve there. And then when it starts to drop back down after we've reached our ultimate strength right there, we have our necking reaching, which it goes until we reach our failure point or our fracture point. Now, this is going to look a little bit different if we're talking about brittle materials. So when you reach failure or rupture of brittle material here, kind of just slowly ramps up, not much of a change here. You're not seeing any spikes and drops over there, no real necking region, and all of a sudden you just get up here and right even there, it breaks before you even see it start to curve back down again at all. So you hit that at rupture for these brittle materials, and we can see over here in brittle materials a really clean break. You don't see any of that necking coming up into that there. It just goes until you hit that right load and immediately fails. So this is something to think about as we continue on into design of elements and some other courses where you're talking about design work there, is what is the best type of material that you're going to use for your particular application? Do you want something that really doesn't change in length much, no matter how much load, but then all of a sudden could have a catastrophic failure when you reach that max stress up here, there, that max load applied to it? But the whole time during it, you really don't see much necking or much deformation. Maybe that's something that's desirable for you, and that's something you consider in the design, the safety factors of your design as well, is, is that load have a big enough safety factor so it's not going to fail? Or do you want something that is going to give and give and give a little bit, and you don't really care if the length changes a lot, as long as you don't have that catastrophic sudden failure? So different things to consider, and that's why we run these stress strain curves and tensile tests on these materials to make sure that it is something that you can utilize for your application, for your design. So this brings us now into Hooke's law, the modulus of elasticity right there. So we have over here on figure 2.11 a stress strain diagrams for iron and different grades of steel right here. So you can see up at the top we have one that goes up all the way up here. You can see a high stress up there. This is our quenched tempered alloy steel on A709. Then you can see down here high strength low alloy steel. You have to see a little bit different curve going on right there, a little bit more ductile type of material like that as you're looking at it right there. And this is an A992. Then we have a carbon steel, and we can see nowhere near the ultimate stress right there for carbon steel in A36. Then you have pure iron right here. This kind of goes up, and that change. A lot of big deformation there, and then a rupture at the very end way out here. So even within steel, we can take a look and say, okay, what alloy is going to be best for my application? Even though I'm not talking about aluminum here, there's going to be different properties with steel that we're going to need to utilize and take a look at. So we talked about modulus elasticity being rise over run related to stress and strain there. We can rearrange that, and what we can do is we can come up with this relationship here and say that our stress is equal to our modulus elasticity times our strain. Or if we're to move this over here, again, there you have it, our modulus elasticity is equal to stress over our strain. So we got our representation for Young's modulus here is capital E. This is Young's modulus, or what we refer to commonly as the modulus of elasticity. And one thing that we can kind of defer from this graph is that strength is going to be affected by alloying, heat treating, and manufacturing process, but not the stiffness. The modulus elasticity is not. And where we can see that there, as we saw on that other graph, is this linear region right here, this rise over run, is where we get our modulus elasticity from. So even though our strength is affected by all of this here for these different types of steel, our modulus elasticity is not. Next, I want to take a look at elastic versus plastic behavior of a material. So we can say here is if the strain disappears when the stress is removed, the material is said to behave elastically. So how can we relate that to a stress strain graph? So if you think about it, if you're in that linear region and it went straight up during that point there, if you were to remove the stress from it, unload the specimen, and it returns back to zero, that's said to be a purely elastic material there. So when the strain does not return to zero after the stress is removed, then it's a plastic deformation of the material has taken place. So that's the case here. If we go all the way up past this linear region, all the way up here to C, we draw a straight line back down over here, then we can see it returns now to D, which is not back at 0 at A, so therefore a plastic deformation of material has taken place. So what's going on in this here? So we can see down in figure 2.13, this is going to be a stress strain response or curve here of a ductile material loaded, and this is going to be load beyond yield and then unloaded. So we go up, we load it beyond the yield to this point C, unload it, and it comes down to D, so therefore we see that plastic deformation. It's gone out of the elastic region and into the plastic region. So what I want to do now is take a look at some practical applications involving tensile testing, where we want to take a look at failure, stress, strain, modular elasticity of a specific product here in a realistic application. So we saw before when we had that test sample up there before, it was just a pure rod, known diameter, easy to calculate cross-sectional area that we put in, and all we're really going to get out of it is the material properties for that particular type of material that it is there. Great way to double check to see if your machine is set up correctly. So a lot of times those will be used for calibration. Or maybe you have samples of different treated steel. You're taking a look at heat treating, water quenching, things like that. And you need to get the material properties afterwards, so you can use those samples from that in order to get the information out of it. But for this here, what we have is a ratcheting buckle and a ladder strap from a company that I do some research work for and some design engineering work for. So we have the ratcheting buckle right here, and we have our ladder strap right here. And for this particular project, we were looking at different materials and seeing how they would hold up. And we were really interested in, what is the max load? Where does failure occur? And not only at what load or stress does failure occur for these, but also what is the deformation at that point? And what is an acceptable deformation? Do we want something that's more elastic and more ductile, that's going to stretch a lot before it breaks? Or do we want something that's going to stay, not really change length much, but then could have a catastrophic failure and break? And this is where, in the real world, other things kind of come into play, one being temperature. So we're going to get into that later in this module here. We talk about temperature changes. Is this a cold sport application? Is it a warm climate that these are being used in? Things like that come into play there. And those are also things that we can introduce during some of this material testing. You could change the environment, the chamber that this is in, put it in a cold environment, put it in a warmer environment, temperature controlled, change the temperature rapidly, things like that, and see how that changes the material properties for the specimens that you're looking at. So in this case here, we did extensive testing on various models of the ratcheting buckles and different ladder straps. For this right here, I'm just going to concentrate on how we change the ladder straps. We're going to leave our buckle as our constant here to, again, make it a realistic application, because what you can see is there's little teeth on this ladder strap right there. And those teeth fit into teeth right here on the locking mechanism on the buckle, so that's where the load's going to be applied. So rather than just pulling this thing and gripping on both ends and seeing where it failed, we wanted to see a realistic application, because realistically, maybe it's not just going to snap in half and neck and break right like we saw on the rods and the other tensile testing specimens, but maybe these teeth are going to deform. It's a really small area right there and a small lip on that, and we have down here another material on the lip there. The question really is, what's going to fail first? Where is it going to fail? What load's it going to fail at? What's the deformations? So we're going to take a look and see with different types of material here. If this ladder strap was made out of solid steel, then obviously, and this is plastic down here, we would expect the ladder strap really not to see much deformation on the teeth, but the buckle where it locks in there might fail. So we ran a bunch of different tests on this, and then we found a good buckle that we were happy with, that we wanted to run for all of our tests, and then we just changed out the materials. This is all made with injection molding process from different molds for these ladder straps there. A lot of DuPont materials, some Hytrels, nylons, things of that nature that were put in there to see how they would perform. Now, one of the main things when we want to compare that is to keep everything else constant, keep the buckle constant, and even swap out with an identical buckle every time in case there was small deformations from the loading there, and run multiple tests on this here. So you're not just testing one ladder strap, you're testing 20, 30, 40 of each type of ladder strap, each material, and then comparing all the data there. So we designed this custom test rig, try to keep it simple, so we just bolted this in through the hole in the base plate there, through some steel over here. We kept the displacement control mode the same for all these. We did a 1/4 inch per minute, a nice slow rate there. And what we did is we recorded on this machine our load, our time, and displacement. Now from that load time and displacement data, from that we can calculate our stress and strain. We can calculate and measure off of this our cross-sectional area that we're going to need here, our original length, and we can get from the distance our deformation, our delta right there, that it stretches during the testing. So from that there, we could then create our stress strain curves, back out modular elasticity, look at our elastic limits, all those things that we saw in the previous graph from our stress strain curves, we can then get there. But again, be cautious because we recorded load and displacement and we want stress and strain. So make sure we apply the right calculations, the right cross-sectional areas, understand what the original length and the deformed length delta is to plug in to get the correct stress strain curves. So this right here, I left in force and displacement. For my application here, I was more concerned about what is the max load that each of these types of materials are going to be able to withstand before we see failure going on, and which one's going to stretch, and is stretching too much on these here for this application. So we see here, if we used a nylon, it's a less ductile, more brittle material, and we can see it pretty much stays almost in an elastic region all the way up to over 400 pounds, but then all of a sudden, boom, snaps right there, 400 pounds. Very brittle material, and breaks right there, had the highest load and the least amount of displacement right there. So from that there, we could get a lot of information whether we want to use that. Now again, be careful. This is not stress strain. This is force displacement. We would need to recalculate this if we want to back out our modulus elasticity for this here and truly say that that's in the elastic region. We're looking at stress versus strain, not force versus displacement. The curves do look very similar, but you need to make sure that you're in the right units right here in the right axes here and not just force and displacement. So then we compared that to the load and displacement for a thermoplastic elastomer material right here. So we can see we got up to a little over 225 pounds before it broke, but it started to deform right here, you know, really start stretching about 150 pounds in pure tension. Flexible nylon and a polyurethane, pretty much both performed about the same here. Polyurethane was a little bit could take a little bit more load before it broke there. So this was something that we really had to think about for our application of which one would be the best. You know, are we really just concerned with that max load? Are large deformations acceptable for the application we're utilizing this in, and all of that? So this is the application that I personally was using this for. For my company, I design custom weight belts that are incrementally adjustable on the fly using a ratcheting buckle and one of these ladder straps here. So for me, I was more concerned about that actual failing. A little bit of deformation is okay, but I didn't want a ton because as people and lifters brace off of these belts, you really don't want it stretching at all. You really want it locked solid in place. So I decided to go for my ladder straps with a glass-filled nylon, a DuPont ST801 material for these ladder straps there. And I wanted to test these in a realistic application, which is more expanding than pure tension. So as the user braces off the belt, it creates a force, which then creates and puts the ladder strap in tension there. And we can do the calculations to figure out what that pure tension is on the strap, or we can instrument that strap with some strain gauges and things like that. But I was really more concerned about what is the maximum amount of pressure that a lifter is going to do when they crank that belt all the way tight and they brace and push out with their core strength on that. What type of forces are we going to end up seeing translated into that ladder strap there? So what I ended up doing was some realistic testing where I put pressure gauges in. You can see some of these pressure gauges down here, and I'll show some pictures later, were instrumented in people while they were lifting. Some strong lifters that were deadlifting some heavy weights, squatting some heavy weights, where they were really bracing off their belts and had it cranked down tight, and seeing what the realistic pressures were. And then I need to correlate those pressures into what type of load I would see here in this load cell on our tensile testing machine here to make sure I got the same practical applications. So what I did was I put the pressure sensors in line with this here and watched it there and did some calibration to see, okay, if, you know, a lifter had braced off up to a certain pressure there, what did that correspond to a load up here? What I found is I really needed to make sure that I was at least 400 pounds of tension from this load cell reading here in order to make realistic comparisons to the pressure that the lifters were bracing off the belt. Plus I wanted a safety factor in there as well. as well. Maybe some more dynamic loads rather than just a static loading test there. So I really want to put that safety factor in there. So personally, I wanted to see it go over well over 500-600 pounds here. So what I did is I ran this up to a 700-pound tension testing test right here. So I'll play the video for this guy here now. So we can see, when I sped this up, you can see this expanding right there. You can see that crack right there moving up and up. You can watch our force versus displacement curve live right here, 400, 500, 600, 700 pounds right there, and still staying pretty linear and keep rising there. I ended up doing this before and went well over 1,200 pounds. I never was actually able to get this to break these straps here with this one. This one only goes up to 1,000 pounds, so I had to do some manual testing and move to some bigger machines after that. But under the 1,000-pound tension testing right here, I did not see any failures, so I was well within my safety factor limit, going with that DuPont ST01 glass-filled nylon for my strap right there, which was really great to see, because you'll even see lifters breaking the cast lever buckles on the traditional lever buckle type of belts here. So to see that this right here was even stronger than some of those was very promising to see in my initial testing. So we can see over here, this is where I talked about how I did the calibration with some of the pressure sensors, and here's all my data acquisition for the pressure sensors to compare the realistic pressure that we've seen in some of the lifting applications in the gym to what we're corresponding here and seeing on our load from our graphs over here connected to the instrument. So another thing that we want to take a look closely at with some of our stress here is fatigue. So we can see here we have fatigue properties, and shown here on this typical stress and number of curves graph that we have over here. So we can see on our y-axis over here we have our stress in KSI, and over here on our x-axis we have the number of completely reversed cycles right here. So 10 to the third, 10 to the fourth, 10 to the fifth, all the way up to 10 to the ninth cycles over here. For two different types of materials, for our steel, a 1020 HR, and our aluminum, a 2024. Now, something to consider with fatigue testing is this is a real-life practical application. People are going to be using this over and over and over and over again. It's not going to be using once and hoping it doesn't fail. So a member may fail from fatigue at stress levels that are significantly below that ultimate strength. If it's subjected to a certain number of loading cycles here. So this is sometimes referred to, you'll hear in common terms of life cycle testing right there, where you think about, okay, if a lifter goes into a gym with my weight belts and they're going to maybe do in an exercise set 10 to 20 reps, where they're going to be bracing against that 10 to 20 different times. They're probably going to do that, let's just say, for 10 exercises. So let's just say there's going to be 100 cycles a day on average times 6 days a week. So that's 600 cycles a week that they're going to be putting on that belt, taking it up to, let's just say, 200 pounds equivalent from the pressure on that tensile testing machine. And for how long? So if we can see that there and we say, okay, it's going to be 600 times in a week, and we run 10,000, 20,000, 30,000 cycles, and we see when it fails, if we only take it up to that realistic 200-pound tension load, then we can put a life cycle, a limit on that, and say, okay, this belt has been tested to use for an average lifter 6 days a week in the gym for 3 years before you're going to see any failure. So I can put a warranty on my buckles and ladder shafts for that amount of time. So this really does tie directly into your ME 171 course and future courses where you're talking about design work. This information you can get from the stress strain curve in these tension tests and life cycle testing, cyclic loading in this case here, where you're taking it and reversing this cycle right here. So this would be cyclic loading on this here, becomes very important. Now, another thing to think about with this here, when you're talking about cyclic loading, is how quickly you get up to that. This, in my case here, 200 pounds on that there. It's not something that I want to go maybe at that 1/4 inch a minute. Maybe something that's, you know, every 2 seconds. Every second I go up, bang, bang, bang. So all of a sudden you might not be able to use one of those lead screw machines. You might need to get into one of the hydraulic or pneumatic testing machines there, where you can quickly do that and do 3 years worth of testing over the course of a weekend or something like that and get those in there. But this is important in testing that you want to do. You want to understand, like, not just, okay, if I'd used it once, it's great up to 1,000 pounds plus, no problem, call it a day. Well, no. You got to do this life cycle testing. You got to test for fatigue and see if this is going to affect anything. So let's get into a couple more formulas here and some key governing equations. If we're talking about deformations under just pure axial loading, again now, go back to our really simple diagram over here, undeformed and deformed axial loaded rod. So uniform shape, uniform cross-sectional area here, original length L, some deformation delta here, and some external load applied to it P here. So from Hooke's law, we can get modulus of elasticity out of this here. So we have the stress is equal to our modulus of elasticity times our strain. Right there, we can rearrange this and say, okay, if we want to calculate strain, we can take stress and divide by our modulus of elasticity. Well, we know a relationship between cross-sectional area, strain, and load that we've seen before. So we can plug in here our stress right here is P over A. So we can replace this with a P over A or load over area to get our stress right there. And we get this now relationship. The strain is equal to load divided by our cross-sectional area times our modulus of elasticity. So from our definition of strain, we recall now that we have strain is equal to our deformation over our original length L. So we can rearrange, plug in these two equations right here, and equating, we can find that deformation right here is equal to our external load times our original length divided by our cross-sectional area times our modulus of elasticity. With variations in loading, cross-sections, material properties here, we can put this into a summation over here with all our indices I. So real simple case here, just for this loaded and unloaded axial rod, going from Hooke's law and our definition of stress and strain to get our relationship for deformation here. So now I want to take a look at a concept application here. So we can see in our diagram right here, figure A over here, we have this rod set up here where we have a cross-sectional area from A to C of this diameter here where the cross-sectional area is 0.9 inches squared. Then we go from C to D, we have a smaller diameter down here, so a smaller cross-sectional area of 0.3 inches squared there. Now we can see we have a load applied here at point B of 75 kips, and we have a load applied here going in the opposite direction here at C of 45 kips, and then over here at D we have an external load of 30 kips right there, and we have locations for all of these relative to where it's fixed here. So point B is 12 inches away from that wall. Point C is 12 inches from B, or 24 inches from our reference point over here, and we have a distance of 16 inches between C and D. So this is something where it becomes very important right away. If this is a problem we're actually going to solve out by hand, where we really want to establish, okay, what is my coordinate system? Am I going to use a standard XY coordinate system here where I'm considering Y positive going up, I'm considering X positive going over to the right, so therefore the load at D is positive X direction, load at B is positive in the X direction, but my load at C would be in the negatives. This helps keep track of sign convention there. This is really a 1D problem, so we're not worried about this, but there was a load added to this when gravity acting in the positive y direction or negative y direction for something like that there. And then we have our reference plane over here. We're considering this to be our 0, 0 point down there, so everything is going to be reference positive moving in our positive x direction off the 0 reference plane over here. So those are just things that are important as you're thinking about setting this up. So now within this problem here, that's what I'd like to do. That thought process right there was a little insight to how I attack problems. I look at it first and try to get as much information as I can just from that given diagram, whatever the problem statement is. Then I come down here and see what they ask me. So now that I have a good idea of what I'm looking at, I know that they want me to determine or find the deformation of the steel rod shown under the given load. So I know the given loads are from that diagram there. Now I know the material type is a steel rod. And this may be something if they told you the type of steel, type of aluminum, type of material, you go to a lookup table and get even more information than you could utilize for this problem. And what I'm looking for is that deformation. So now we've seen relationships, equations from Hooke's law, stress and strain, of how we can back out deformation. So this is a complicated geometry, complicated object right here. So the thing we want to do when we start talking about our solution here is divide it up into individual sections. That's the best way to attack it. It's not overwhelming. We can break it down piece by piece and put it all together. So we can divide the rod into components at the load point, load application points there. So you can see load application points are B, C, and D. So we can deal with each of those separately there. Next, from that point there, once we divide it up into those individual components of the whole system, the whole rod there, we then can apply free body diagram analysis on each component to determine the internal forces there. So we can do our traditional free body diagrams that we've seen in statics, dynamics courses. Same thing comes back again. So we break it down, draw those out. And again, that's where we're coming up and establishing our coordinate system, our reference points, all that becomes very important. And then from there, once we have our free body diagrams, we can evaluate the total component to deflections from there. We can do our summation of forces, bring in Newton's law. All those things can come into play there as we're doing out our free body diagrams. From those forces, we can go back, calculate our stresses, our strains, modular elasticities, and in the end, our deflections using all those governing equations. So now we'll do the first step where we divide the rod into its three components there. So we take a look and we'll divide in between point A and point B. We'll put this as point 1 right there, right in the center of that, right there, where B is our load. 75 kips. Then we'll go between B and C here, and we'll draw a line in the center of that there. We'll call this point 2. And then between C and D in the center of that right there, we'll call this point 3 right there. So let's just deal with the tip of this first, farthest away. We can see we have this load here of 30 kips at the end of this here. So if we cut this right down the middle, we have this section right here. So we can see we have 30 kips there. So we have one load going this way, one going this way. We could do our summation of forces in this here. And what we find out is we have just two forces on either side. We could do F equals MA, go through all of that there, but we see 30 kips there. We have 30 over here. So P3 right here is going to be that 30 kips. Convert this to pounds, which is a more common. So we do this times 1,000 there. So we end up with 30 times 10 to the third for our load at P3 right there. So now we do the next one here. We divide it down here at point 2. So then we can see, well, we have all this here from C to D, and then from C up to point 2 right here. So we have our load P2 right here acting at this point where we section this off right there. So now we can see, and again, this is something important. We really want to draw out that coordinate system we're using. We're considering X positive to the right, Y positive going up. We're really only in 1D here, so we're considering X positive right. So that's why this guy right here, we can see now we have 30 kips going this way, so this far over here. If we have 45 going this direction at C right there, so therefore we're going to have a negative 15 for P2. And you can see the reason that that's negative here, if we look at this, our C is going in this negative direction right here, so therefore the C is going to be a negative 45 kips, but a positive 30 kips, so that becomes a negative 15 times 10 to the third pounds right there. Then we do our last section here, so we're going to break into 3 sections. So now we come down here to 1 right here. So this is the entire thing there. So we have this 30 kips positive to the right, positive X, negative 45 going to the left, or negative X direction right there. But then we have 75 kips right here going over to the right there. So we have 75 minus 45 plus our 30 right there. So we end up with this guy here, when we do this out, is that we have a P1 in the end over here. When we do our math out of 60 kips, or 60 times 10 to the third pounds. So this is all from doing our free body diagrams. Again, it was really simple. I didn't take the time and draw F equals MA for all 3 of these. But for a more complicated one where there's other loads, maybe there was friction involved, drag forces, different things like that. We had 2 different directions rather than just a 1D problem. It was a 2D problem. Therefore, each one of these, you want to say summation of forces of masses in the X direction, summation of forces is equal to mass and acceleration in the Y direction, all that stuff from Newton's second law, and apply that to go through to calculate and solve for your P1, P2, and P3. This one was pretty straightforward, so I could infer those directly from our diagrams to get P1, P2, and P3. Now, the other thing that we're going to need that we've seen before is our length. So we say our L1, L2, and our L3 right there, where our L1 and L2 were equal given to us in our initial diagram. Those were equal to 12 inches each. Our L3 was given to us as 16 inches for that length right there. So from that there, we can then calculate our area. I'm sorry, not calculate area. We can then go back to our initial statement and get our areas right there. So area 1 and area 2 was given to us in this problem statement here. We don't need to calculate it from any dimensions here. It was actually given to us as area. So A1 and A2 were both that same cross-sectional area, and that was 0.9 inches squared. And A3 was given to us as an area of 0.3 inches squared based on the cross-sectional area of this smaller diameter down here. Now from that there, we could go into that equation that we solved for earlier for our deformation here. So our total deflection here is equal to delta is equal to the summation of all of our loads times the original lengths divided by the areas divided by the modulus of elasticity right there. Plug that in. We can see the 1 over E doesn't change. The modulus of elasticity doesn't change. It's the same for all of them. So we can pull that over out front over 1 over E. So then you have 3 different sections here that we're summing together. So we have section 1, section 2, and section 3. So we have our load times original length divided by our cross-sectional area. For 1, plug those values in. Well, we have our P1 given to us as 60, or sorry, that we figured out to be 60 times 10 to the third, plug that in there. Our L1 is 12 from down there, and our A1 is given to us as 0.9 inches squared. Then we do the same thing for our P2 over here. P2 is calculated as negative 15, again, because this is going in our negative x direction right there. We have a negative there, times our L2 length, which is 12 inches right there, divided by our A2, or our cross-sectional area 2, which is 0.9, plug that in there. Then we go into our third section here, P3, L3, A3. So P3 we found to be 30 times 10 to the third. Then we have our L3 of 16 from this right here that we can plug in there, divided by our A3, which is 0.3. Plug and chug through all of that there. 1 over E times the summation of all of that is equal to 75.9 times 10 to the negative third inches. So that is our deflection that they asked us to solve for, 75.9 times 10 to the negative third inches. Double check your units, make sure everything is correct. But a pretty straightforward problem for this conceptual application. So next we're going to take a look at is static indeterminate problems. So these problems occur when there's structures for which the internal forces and reactions cannot be determined from statics alone. These are then said to be statically indeterminate. So a structure will be statistically indeterminate whenever it is held by more supports than are required to maintain its equilibrium. So over here we can see in figure 2.23 we have an example of that there, where we have more supports than required to maintain its equilibrium here. So you have these internal loads at K and D right there of 300 kilonewtons and 600 kilonewtons as pushed down on this base platform that's sitting on there. Then you also have a contact point up here at point A. So as this is pulling down from this point up here, where it's connected to the ceiling at this a pivot point right there at A, it can't go any further because it's got B as well. So this makes it statically indeterminate because there are more supports than required to maintain equilibrium. You could remove B there and it could maintain equilibrium with these loads, 600 kilonewton to 300 kilonewton low, but with this B here, it has that redundant load there. So redundant reactions are going to be replaced with unknown loads, which along with the other loads that we see there must produce compatible deformations. So these deformations due to the actual loads and the redundant loads are determined separately and then added together. So the deformations from the actual loads right here is what we're considering our delta L, and the deformations from the redundant loads over here is what we're considered our delta R. So the total deformation right here is equal to the deformations from the actual loads plus the deformations from the redundant loads, and these are going to be equal to 0. So we can see in the diagram A up here at the top, we have this restrained axially loaded bar. In part B, the reactions are found by releasing the constraint down here at point B. So you can see we release it at point here, right at point B, to enforce this 0 deformation at point B now according to this relationship. Next, let's take a look at this concept application 2.4 here. So in this here, we're using that same problem we just looked at here now, where we have the statically indeterminate problem here, and they want us to determine the reaction at A and at B for the steel bar and loading that's shown. We're going to assume a close fit at both supports before loads are applied. So before this 300 kilonewton, 600 kilonewton load, we're assuming that there's going to be a close fit. We can see A is up here at the top at that reaction, and B is down here like this here. So for our solution, here's how we're going to solve this problem. First, we're going to consider the reaction at point B as redundant. So we already discussed that. This can still be at equilibrium even without point B there. Point B is kind of preventing it from deforming down there. So we release the bar from that support at point B and solve the displacement at point B due to the applied loads, is 600 kilonewton and 300 kilonewton load right there. Then from there, what we're going to do is solve the displacement at B due to the redundant reactions R sub B. So we can see down here in diagram B, there's your reaction at R sub B right there. So we can solve for the displacement at B due to that redundant reaction there. Next, we're going to use that relationship we saw earlier and require that the displacements due to those loads, or 300 and 600 kilonewton loads, are due to the redundant reaction be compatible. So this right here means that we're going to require that their sum be 0, as we saw in that previous relationship. From there, the next step will be then to solve for the last unknown there, our R sub A, which is the reaction at our, due to the applied loads and the reactions that we already found. So we're going to use what we found for R sub B to plug back in and solve for our R sub A. So now continuing on with the solution for this problem here, the first thing we want to do, just like we did in our previous example problem, is to break this down into individual sections and solve it piece by piece. So we can do that there by breaking it down into 1, 2, 3, and 4 sections right there. Solve for the displacement at B due to the applied loads with the redundant constraint release. So you can see it's released down here at B. So we just have the individual internal loads here, our 600 kilonewtons acting here at K, and our 300 kilonewtons acting here at D. So that's why we break it in from A to D, D to C, C to K, K to B. So just like we set that up before, we can do out our free body diagrams. And from those free body diagrams, what we can find is that we have no external load here down at the bottom of P1. So P1 is equal to 0 when it's released. Our P2 and our P3 are going to both be 600 times 10 to the third kilonewtons there from our load right there. So you can see our 600 acting right there. We then have our P4, which is going to be our 600 plus our 300 kilonewtons when we do out this free body diagram in our equations, summation of forces. So that's going to be 900 times 10 to the third newtons there. We also know our areas there. We can see that A1 and A2 both have that same cross-sectional area right there. So this is going to be our 400 times 10 to the negative 6 meters squared. Make sure we get our units right there. We're in meters. Our A3 and A4 have the same diameter at 3 and 4. So it's the same cross-sectional area there of 250 times 10 to the 6 meters squared there. And then what we can see, the lengths we have are all the same. Our lengths are L1, 2, 3, and 4, all that 150 millimeters. So again, pay attention to your units as you're solving this out. Millimeters needs to be converted to meters. So L1 equals L2 equals L3 equals L4, which is 0.15 meters. Now from there, we can solve for our delta L. This is summation of our loads times those lengths all over our area, cross-sectional areas times our modular elasticity. So we've seen in the previous example, skip a couple steps here. This example is also in your textbook to go through and reference as well for the details. We do that out, plug those in for all the individual loads, or P1, P2, P3, P4. Pull out our 1 over E for the same and modular elasticity for everything out front of it. We do that and we find out when we add all of our loads together, divide by our areas there, we end up with 1.125 times 10 to the 9th divided by our modulus elasticity right there. So that is our delta given by this expression here, so our delta L. From there, we can then solve for the displacement at B due to the redundant constraint. So we can see now we have down here in our diagram, we put this back in right there, R sub B. Now we're breaking this down into our two sections right here. The bottom section from C to B here is 1, and from C to A up there is 2. So now that we're looking at the two sections, rather than being 150, we saw up there, 150, 150 is 300. So from C to B is a length of 300 millimeters, and C to A is 300 millimeters as well. So now what we can do is we can say our load in 1 is equal to our load in 2, our internal load here. So we can see that if this is all 1, or sorry, this is all 2 and this is all 1 there, our load in 1 is the 600 kilonewtons. Our load up here, P2 right there, and our P2 up there is equal to the negative R sub B right there from the redundant constraint down here. So our R sub B, you can see the reason this is negative is the opposite direction right there. So this is again something where we want to say what's positive going up, what's positive going down, and be consistent with that so we get our sign convention correct. Now our area in 1 and our area in 2 are different. So our cross-sectional area for A1 and A2 are different. For A1 down here, cross-sectional area is 400 times 10 to the negative 6 meters squared. And our cross-sectional area in 2 up here is 250 times 10 to the negative 6 meters squared. So from that there, our next step is to then look at our length. So again, we just mentioned this L1 is equal to L2. These are both equal to 0.3 meters. Again, we convert to meters. Everything else we're dealing with is in meters as well. We want to make sure we convert from millimeters to meters. So rather than being 300 millimeters, this is 0.3 meters. From there, to calculate our delta, we can then say our delta R is equal to the summation of our individual loads times our lengths divided by A times E. So again, we can plug into that, do out the summation. Again, there's two sections here. We do this out. We end up with is we have a negative here now because we had a negative value up here for our negative R sub B there of 1.95 times 10 to the third times this R sub B over our modular elasticity E. So to continue on with the solution, we go back to the relationship we showed earlier that where delta is equal to our delta L plus our delta R, which is equal to 0 there. So now we can plug into that there. We've solved for our delta R, our delta L right here from the first part of that problem on the previous slide there of 1.125 times 10 to the 9th over our epsilon. And we solve for our delta R right here of negative 1.95 times 10 to the negative sometimes 10 to the positive third times r sub b over that epsilon there is equal to 0. So you can see this is a minus sign there because this value for our delta r was a minus sign on the previous page right there. We can plug this in and we find that our delta is equal to 0 for that there. So for our delta to equal 0, our only unknown right here is our r sub b right there within this relationship there. We can solve for our r sub b within this now, and we can see that our r sub b is then equal to 577 kilonewtons once we back that out of that relationship. So then we can do the last step of this, which is to find the reaction at A. So we can see here in diagram here, E over here, there's our reaction at A, r sub A right there. And this is due to the loads and the reaction at B right there. So this, again, we can do out of free body diagrams, summation of forces in the y direction where we're considering right here, our y direction to be positive going up is equal to 0. From Newton's second law, we can do that there. And this is equal to, we look at our free body diagram, what forces are acting on this? Well, we have our r sub A in the positive y direction, our 300 kilonewtons in the negative y direction, our 600 kilonewtons in the negative y direction, and our r sub B in the positive y direction. We do our sign convention correctly, so our summation of forces in the y is equal to 0. At equilibrium is equal to r sub A minus 300 kilonewtons minus 600 kilonewtons plus 577 kilonewtons. Only unknown in here is our r sub A. We can solve directly for our r sub A. R sub A is equal to 323 kilonewtons. So therefore we have our r sub A and our r sub B. We write these down. These are the things that they asked us to solve for in our problem statement. Write them out separately and box them at the end. R sub A, 323 kilonewtons. R sub B, 577 kilonewtons. So the last topic I wanted to look at was temperature change and problems involving temperature change. So if we have a temperature change, this is going to result in a change in the length or the thermal strain. If we convert it to strain there and do the strain calculation, there is no stress associated with thermal strain unless the elongation is restrained by the supports. So what we're going to do with that is we're going to treat each additional support as redundant and apply the principle of superposition here. So we can see the following relationship equations here. So our delta T right here is equal to alpha times our delta T, our change in temperature, times our L there, where alpha is going to be the coefficient of thermal expansion. Whereas we've seen before, our relationship we saw before, our delta P over here is going to be equal to our load times length over our cross-sectional area times our modulus of elasticity. So we have two different relations. We have our delta T from thermal expansion right there from our change in temperature, and we have our delta P from our load over here. So we have both of these now, our delta T and our delta P. So this thermal deformation and the deformation from redundant supports must be compatible. So we have this relationship shown out here that our delta is equal to our delta T plus our delta P, which is then equal to 0. So from that there, we can start plugging in these relationships for our delta T and our delta P right there. And we end up with this relationship down here. Now we have our alpha, or our coefficient of thermal expansion, times the change in temperature, times L, the length, plus our, now we plug in for our delta P over here, our load times our length, divided by our area times our modulus of elasticity equal to 0 there. We can rearrange this here, solve it for our load P. P is equal to the negative cross-sectional area times our modulus of elasticity times that coefficient of thermal expansion times our delta T, our change in temperature right there. Or we could break this down and realize, okay, well, if we want to look at stress here, stress is equal to load over area. So we can take this area, divide it over to this side here, and this load over area then becomes stress. So stress is equal to the right-hand side of what's left over here, which is our negative modulus of elasticity times our alpha term for our coefficient of thermal expansion times that change in temperature right there. So that now gives us a relationship that we see here.